Alrighty, for your lab number 1, it's due tomorrow. I believe it's midnight, so please double check on the PDF. The submission deadline will be very strict, guys. Submit your best attempt. If there's anything you cannot really complete by the submission deadline, still submit something. Submit your best work before the deadline to claim your credits. And then after the submission deadline, I will give you guys some solution. You can take a look. Next Monday, I will try to also maybe go over the solution a little bit with you guys, just to make some highlights so you guys can watch out for something for your test. I'm also going to release your lab number 2, definitely before Monday's class, so I can also give you some guidance about lab number 2. Because lab number 2, the format is going to be very similar to your upcoming programming test 1 and 2. I think that's going to be a crucial lab. And speaking about your programming test, let's look ahead a little bit, right? I think this will be the plan. I'll also put it in writing a little bit later, but I just want to mention to you guys. If you look at the semester calendar over here, all right. So we are lecture number 6. We're here today. Time flies. We are finishing week number 3, but we'll definitely get to the temporal logic kind of stuff, right? Which is setting up the context for this course, which is important. All right, so your programming test number 1 will be right before the reading week, right? So that one there, we will be expecting you to be quite familiar and proficient with the Pascal syntax. So you definitely want to make sure you can explore the resources I provided in lab 1 instruction. I'll repeat those resources again in lab number 2. So for lab number 2, you can expect to start maybe around this date. 2 weeks is more than enough for you to really complete lab number 2. After lab number 2, I will also go over the solution with you in detail because there will be some tricky predicate you have to understand in order to write a programming test. But struggle through them. You can definitely reach out to me even before submission deadline. But I will definitely give you guys a walkthrough also on the 10th before your test. Mock-up test, right? That's something I promised. I think the best timing to hold it would be on the 6th. All right, so there's a Thursday here. So you can mark down on your calendar. So February 6th. Again, attendance will be optional. You don't really need to come. But if you really want to just take the mock-up test to kind of experience what the lab test is like, you may have taken lab tests from other courses anyway. But just come. I'll set up the machines just like the lab test. And then I'm just going to give you the example test question I will give to you anyway. But you can try it out for the first time. All right? That's what we will do. And then also give you guys some guidance beforehand. So you can also get some idea about what the test is about. All right, that'll be the idea. 6, okay. All right, and then let's now go back here. And as usual, my office hour doesn't change, the same. Okay, I'll just keep reminding you guys, if you want to speak to me, feel free. If that really clash with your class hour, just reach out, and then we can set up some time. That's not a problem. And for TA, for Andy, just keep him busy. Right? So if you guys haven't bothered him too much, feel free to ask him questions too. Right? So he took this course before, so he might be able to share some insight with you as well. He might be able to. We'll see. All right, any question about the course? Yeah?
So if you're not able to come on the 6th, are you going to post sample test online?
You mean the mock-up test, right? Yeah, so I'm going to post the question anyway. I'm just saying for people who actually come physically, you can also try it out, right? So I would say even if you really cannot make it to mock-up test, the look and feel of the test will be just like a remote lab environment. So you can also simulate by yourself, right? No problem. I'll definitely make sure it's fair to everybody. Yeah. Alrighty, if no further question, let's now, hopefully we can finish the math review today, for sure. I also got some exercises to try it out together with you at the end. Okay, let's now go over into predicate. Oh, sorry, before that, let's do recap very quickly. All right, so last time we already started a review, especially we finished this, we kind of used the quantification, but we're going to talk about it more today. We're using for all and also exist to kind of a model or formulate the model checking problem. Guys, you can take a look. That's really something that's important to understand conceptually about this course, right? And also reachability graph, very crucial. And we talk about this exercise over here about comparing the short circuit evaluation versus commutativity in math, right? So in programming, the order of the predicate to be evaluated or proposition to be evaluated, the order matters. So you might run into some runtime exception if you put the order wrong. That's what we are talking about. So it wouldn't be an unreasonable question if I put on the test to say, let's say given this particular organization, let's say this particular order, I want you to tell me, number one, is it going to work all the time? Number two, if you don't think that's going to work all the time, give me the precise input scenario where the exception might be triggered, right? That's what we discussed last time, right? That's what you really pay attention to. All right, and then we spoke about imprecation. That's just an analogy for you, but just remember imprecation is very important. So when we get to temporal logic and also program verification, we always need imprecation. And imprecation usually will be the tricky case to actually prove. Okay, we'll see. And these are all the 4 cases, right? So the only case that's going to make it false is when the antecedent is true and the consequence false. That's the only row. But for the other 3 rows, you also need to understand how to understand them intuitively. And we spoke about different ways for describing the implication, right? For example, if you say P implies Q, that's really the math form. And then we can say Q if P is sufficient for Q, and etc. We got 1, 2, 3, 4, and 5. 5 different ways to really describe the same thing, right? So the way to really study for this, which I really hope you can go beyond this course, is to really try to look at each one of them and see how that particular description is going to correspond to all the 4 rows in the truth table for implication, either explicitly or implicitly. We'll talk about each one of them in detail last time. If you got any doubts about it, reach out. I can explain again. But I think this page here is important. Of course, I gave you some very oversimplified problem which I might give to you in the exam or in the written test. I might just give you, for example, something along the line about implication. Right? I may not write it out explicitly, but you should really identify that as implication. And then I might just give you some choices to tell me which one will be equivalent to what I described in the question here. Right? That's something we also said last time. So you just got to be very clear about the possible ways to describe implication. And this one here is also very useful. Whenever you want to prove about equivalence, you can separate equivalence proof into 2 ways, right? If I want to say P is equivalent to Q, I can say P if Q, and also P only if Q, right? So these are the 2 directions. You can also look at these 2 as well, right? When we get to program verification, we might see some cases like this, but anyway, or even temporal logic. But it's a very general form. All right, so we talk about different manipulation for implication. We got inverse, converse, and contrapositive. And don't forget, we got some very useful theorem about contrapositive, right? Okay. And then we got identity 0, right? That's also good. Natural number, right? Includes 0 for this course, just in case you don't know. And then we got some comparison. Okay, I think that was the last page. So we're going to talk about the mathematical meaning for quantification just for review purpose to make sure everybody knows how to interpret them. Because later on, when we actually want to define the formal meaning for temporal logic that involves certain timings, so that'll be more like a new way of thinking about like a system, right? So that's something we'll get into pretty soon. In order to define different operators for temporal logic, you will need to understand like for all or exist. That's something we'll do. Okay, so this is what you guys learned back in 3342. You can think about these 2 symbols are only for your information if you want to compare. But for this course, especially for your programming test, you are actually going to write something along this line, right? So remember that syntax document I referenced in lab number 1, right? About the cheat sheet I'm going to give to you. So get yourself familiar. Anything that's described there, you don't need to memorize. You can just go to the test and make sure you can look it up. However, there might be certain syntax you know that is legal, but it may not be in the document. You may have to memorize them. I'm sorry. Right? Just make sure you have to know them, right, for your test. Right. So when you get to lab number two, you will see more about the usage of this. Right. I also speak about it a little bit more, maybe on Monday. All right. Let's now get to practical logic more about quantification. Right. Just review the syntax and also about the syntax meaning, and also examples. Okay, that will be the goal for today. And I'll also do a little bit of proofs, just to let you also get familiar with the formats about equational style. All right, we'll talk about predicate, and it is important to know that we do have some universe of disclosure, really like a range, okay? So the way you specify that, right? So let's now take a look. Oh, just one thing to also mention, right? This is also important for you to note. Usually, so when we talk about logic, right? So let's say quantification. Apparently, the syntax may be different depending on whether you're writing that on the paper or you're writing that in Pascal, like a computer, right? So I would say for this course, in principle, for your programming test and also for your assignments, sorry, I should say labs. I got confused with another course. I should really say labs. All right, so for your programming test and labs, you're going to use the ASCII syntax, of course. It should be acceptable to the tool. So the ASCII syntax will be something like this, right? Using these kind of ASCII syntax, right? On the other hand, in the lecture and also in the exam, and also in the exam. And the exam, by the way, will be like a paper test. So if you are asked to write any logic, by default, you should really write in the math form that we discussed on the slides. Okay, so you should really know these two words about the syntax. On paper. However, in the exam, I just want you guys to also get ready. There will be some occasions where I will explicitly ask you to write the logic in Pascal syntax, because I may also want to make sure you understand about Pascal. Right? So that's also possible in some occasion, but I'll be very explicit. By default, it should be the math syntax on paper, but I may also ask you. May also be asked to write in Pascal syntax. Yeah, so you will just don't get confused. Right? You should really kind of separate between, but they are really equivalent. It's just a little bit different way to organize the math, but the essence is really the same. You might be wondering, what about written tests? Written tests will be mostly multiple choices over the E-class. If there's any part that might require certain writing, I'll let you know beforehand. So you can also get prepared. But these are the two distinctions, right? Just very quick. All right, let's now talk about the quantification. So we're talking about on paper, right? So this one here, we got some symbol here. You guys recognize that's universal, that's existential. And then we have some variable list. If you got more than one variable, you might get I, comma, J, comma, K, right? So comma will be the one to separate, right? You'll see example on the slide as well. And we talk about here, so the R over here is the range. That's the universe of disclosure. So this part over here, the R in both quantification. So that one is what we call the range. The range of the variables that we want to consider about the property that follows. That's the universe of disclosure. All right, so these two. And then you want to watch out for the symbols over here. So apparently, this one is something we discussed very extensively, implication. And this one over here is the conjunction, right? So you will see something similar. Oh, by the way, so in Pascal, as I noted to you last time, they don't really distinguish, but the colon over here in Pascal, for all, they really mean the implication that we just saw. And the colon you will see over there is really the exist. But in Rodin, it's quite nice because they will require you to write it down in that particular pattern, right? But they really boil it down to the same thing. Okay, just for you to watch out for. All right, I'll talk about these two symbols in just one moment, okay? And then the P over here and the P over here. So these are the properties that we are interested in establishing. Okay. Properties Okay, just properties, like another predicate. All right, so let's now talk about I'll get to the special cases for range, but let's talk about the meaning just in general. All right, so now for this particular implication, I'll put star here. Okay, I'll put it here. So the star here is going to be the meaning for universal quantification. So there are two cases. You can think about for implication. We say that if the antecedent is true, then we have to worry about whether the property is true, right? That's the identity, if you remember. On the other hand, if the range is already false, we don't really care what this is, right? So these are the two cases, right? So for universal quantification, you want to think in terms of two cases. So number one, if the I value we are talking about is in the range, i.e., R of I is true. If it is the case, then we have to evaluate the value of P based on that value of I. We have to. If the property turned out to be true, then true implies true. That will be true, of course. If the property turns out to be false, then we got true implies false, which would be false, right? So it really depends. Okay. Then P of I determines if the implication is true. All right. And when we say for every, we want to consider all such I. We're gonna consider each one of them. Okay, and every one of them should be true. On the other hand, the special case here is if I is simply not there, we simply don't care. If I is not in the range, that means R of I, it will simply just be false. Then no need to consider. No need to consider P of I. All right, so these are the two cases, right? All right, so let's now talk about existential. So now it's simply conjunction. That simply means it must be both in the range and also in property must be also satisfied. Okay. So that one there is more straightforward, but I'll just put it down anyway. Okay, let's say star star. So star star. So I should be in the range and P of I should also be true. And the exist over here tells us we should find at least one such I. That's called a witness, right? Conjunction here. All right, let's now talk about special cases over here. So let's talk about what if the range over here represents an empty range. Okay, so that's also important. So let's now talk about, let's say, R of I here. So you want to think to yourself, what if R is an empty range? So that means R of I is simply equivalent to false. And this one here really is to say there is no such I that's going to satisfy the range. I'll give you one example right away. So one example here would be, what about the range? It can be a conjunction. Let's say we are constraining integer. You might say I larger than 10 and I smaller than 5, right? It's not possible to find such I. So this particular range over here should be simplified into just false, right? Just one example. If the range predicate is such that there's no such value that will satisfy it, then it's empty, all right? And whenever you actually, if you somehow whatever formula that you want to kind of establish, for the universal quantification, if somehow you can argue that the range is already false, then you should feel happy, because once this is false, we know false implies anything. We just evaluate to true for the implication. We'll just get true. All right. This one tells you that, okay, this one, I'll write it down. So whenever you say for every I, and then if the range is simply false, and doesn't matter what P is, the whole thing will just be true, trivially. The whole thing here will just be true, trivially. Okay, this one let me just say once more. So we are talking about universal quantification, in which case we have to worry about all the values of I that will satisfy the range. But what if there's no such value that's going to satisfy the R? In that way, we will simply get false in this case. So now false implies anything will just give you true for the implication. So that means that universal quantification here will just reduce to trivially true. So that's one of the cases you will hope. That's what you have to deal with. All right, so that's one. And it will be kind of symmetric for the other one. Okay, let's say for existential over here, what if the range is actually empty, right? So let's also talk about it. Okay, and then I'll give you a little bit more programming example, and then we're done with the basic review. Let's say for this one here, let's say here. So we talk about the range for existential. Okay, I'll put it here. What if R is an empty range? Right, for example, you can think about this one here. Okay, empty range simply means we cannot, because what? Existential will be true if we can find at least one value of I that's going to be in the range. But there's no even such a value in I. So conjunction is going to kind of fail. It's going to be false, right? So the whole thing is going to be false. That's also a trivial case for us. So that means R of I is equivalent to false, right? That's something just like the universal quantification, special case. And that one will just reduce to just false. All right, so that one there, I'm also going to write it here. So if you got exist, I, and then you have the false range. And notice that we're using conjunction here, right? So that'll be false and PI. And we know pretty well this part here, if conjunction on the left-hand side is already false, whole thing will be false. So the whole existential is just false. You just cannot find such a witness. Okay, this will be the final thing to mention. So this will be false trivially. All right, that's a very quick review about the two quantification. So you gotta watch out for what it really means to have implication versus conjunction, and also gotta watch out for special cases for the range when they are simply empty. All right, that's something you gotta watch out for. All right, if no further question, I want to mention very quick two examples just to show to you how this can be somehow applied. Maybe you have been applying it, but never kind of realized it was the case. Okay, so let me put it aside over here. So let me do the following. Let me separate that. Okay, I'm going to give you two Java methods over here. Of course, I'm not going to program the whole thing, but you will get an idea. Let's say I got two Boolean methods here. Say the first one is, let's say, Boolean And I want to check to see if my input array contains all positive numbers. It's called all positive. And then I got some integer array. Let's say numbers, ns. Okay, this is the first method, right? I'll give you a little bit more details. But let's compare the two methods right away. I got another Boolean method here, which will also take another input integer, like an array of integers. But now that one there is going to say some positive. Is there some positive number in the array? So that's more like an existential quantification idea. So that will be some positive. So integer array ns. All right, I'm pretty sure you guys know how to program these two methods either iteratively or recursively. Okay, I'm gonna leave you to that, not a problem. So what I want to focus on will be, what about the special cases where the input array is empty? That's where we can draw the connection to the logic, right? That's what I want to bring your attention to. I'm gonna write it down over here. So let's say if, let's say array is ns. ns the length equals 0. And over here, I can simply return something. And similarly, here, if I got, okay, let me just copy this. There we go. All right, so I got two kind of base cases in each method here, right? All right, guys, any idea? What should this be? If I want to check if all the numbers in the array is positive, but now the array is empty. True, okay? Because that one there actually nicely corresponds to this case over here. You can think about, in order to return true, then all the numbers in here, that should be true. But there's no such number. That means I cannot find any counterexample to prove that there's no number in the array that's actually negative, not positive. So I cannot disprove it. So it must be all positive. I'll write it down. Return true. Okay, the reason is cannot find a witness violating the, so here when I say positive, just positive property. You cannot find anything that's not positive because it's empty. You cannot find anything to disprove it. Okay? So that's more like when this here, this range here is empty, then in that way, the implication will just be true trivially. That's where you can draw the connection. All right? All right. Similarly, this one here, which is return false. Because for existential, you're supposed to find a concrete witness to show that the property can be satisfied. But now if the array is simply empty, you cannot find such concrete witness. So that should be false. All right? All right, that's good. Cannot find a witness satisfying the positive property. All right, so that's kind of basic stuff, but it's good to make sure everybody kind of understand about the basics, right? And of course, there will be occasions where you may have to write nested quantification. That might be something you will encounter, I believe, in lab number 2 a bit, where you have to write more like a post condition for the procedure. That's something you will have to do. All right. So something I want to also mention very quickly, right? I don't really have any example about nested quantification in the slides, but I'll just give you some quick principle, right? So when we talk about, let's say just say for all. So we talk about nested quantification. So let's say if we say for every I, So R of I, and then we say some property Pi, right? That's how we started with. This part over here can also be complicated. It does not need to be a simple form. That part there can also be a predicate. All right? So this part here, I can simply replace it and say that one I can use parentheses to kind of force the order of evaluation. So that part is going to be more like a property part or body part of the universal quantification. And that one there, you can just introduce another exist, maybe J, right? And then I can say Q, just another range predicate, okay? And the Q here, I can actually make use of both the I and J, because I somehow is also visible to the inner one, right? So I can, maybe somehow I can say I here and J here. And also maybe another property, maybe R. I don't know, maybe S. Right, so this is just to show to you, you don't really have to have unnested quantification. It's definitely possible. So when you actually get to Pascal, you can follow a similar principle. You just gotta work out the syntax, okay? All right, so this is range number 1, this is range number 2, right? So these two are the ranges. All right, and for the precise syntax, once we get there, we can discuss it. But that's just the principle. Okay. Okay, let's now move on and do some example quickly. And then we're going to talk about how you can prove and disprove the quantification. All right, so I think we cover everything here. You guys can also take a look at the slides. And then, okay, universal quantification. Yeah, syntax over here. Okay, let's look at the example. Okay, very easy. All together. All right, examples. All right. All right, let's start with this one here. Right, I'll let you guys read it and tell me whether or not it's true or false. True. Okay. So I'm saying here, I only care about natural numbers starting from 0. I'm saying all the numbers in the range, 0, 1, 2, 3, 4, all the way, all of them are larger than or equal to 0, obviously, right? So in this page here, we don't need to do anything formally. We're just trying to informally judge whether that should be true or false. But once we talk about proof strategy, we'll do a little bit more example just to see how we can prove or disprove it. But for this one here, you can think about this one here tells you it's going to be 0, 1, 2, all the way to plus infinity. As you can see, 0 larger than or equal to 0, true. 1 also larger than or equal to 0 and all the way, right? Obviously, all the numbers in the range satisfy this predicate property. So it should be true. This one is rather easy. Maybe next Monday, since I already talked about nested quantification, let me prepare some new examples so I can give you some maybe nested quantification we can also judge. Maybe some. All right, maybe next Monday I can prepare some extra. How about the second one? False, right? Okay, so why would you think that's false? Negative, right? Yeah, exactly. Very good. Yeah, you guys are good. Yeah, because I know that this range over here, we got to consider all the numbers in the range. It does include, for example, minus infinity, for example, minus 2, minus 1, and also plus, right? For example, if I choose the minus 2, and minus 2 larger than or equal to 0 is false. So I got exactly the true implies false, which will be false. And this is a little bit about how you can disprove a universal quantification. A little bit look ahead. You basically have to find a value, for example, minus 2, that's in the range, which will make the range part true. And then that particular value in the range is going to make the property false. That's how you get true implies false, which will be false. That's how you disprove it. Okay? Look ahead. So overall, this will be false. And how about here? I heard true. Okay, false. Why false? Yeah, exactly. Very good. Yeah, just look a little more carefully, right? So here, this one here, you can see where you say I comma j if you got more than one variables, right? So here we are saying for all the combinations of I and j, both I and j are just any negative, 0, or positive numbers, right? We're saying for all these numbers, it's either this or that, no third possibility. But apparently there's a third possibility. They could be equal, right? So now I can just give you something here. For example, let's say for I and j, what about I just have 2 and 2, right? Now I can see 2 in in integer and also 2 in the integer. This part here will just be true. On the other hand, if I say 2 less than 2 or 2 larger than 2, apparently both false, right? So I'll just get false. So what I'll get is true implies false, which is equivalent to false. That's why it's not the case for every combination of I and j in the range. All right, false. All right, so we have seen actually 2 different cases here. Either we want to disprove it or we want to prove it, right? We'll try to make the steps more concrete for you to follow. Okay. All right. Existential in some way will be easier if you know what's the witness right away. This one here, true. Okay, how about that? Let's not bother you. You just tell me which one can make it true. For example, 0, right? So here, if I get simply 0, so 0 is a natural number that's true, and 0 larger than or equal to 0, true and true, of course, it's true. So true and true is going to give you true. That's the only way to actually make the existential true. You got to find exactly one value in the range and also satisfying the property. So this will be true. This one here, true. This one is interesting. If you compare, for example, this one here and also this one here. So here we got universal, but we got existential. The nature is different, right? Okay, I'll just highlight it. This one here and also this one here. All right, true, good. Easily find one. I can say 0 is integer and also 0 larger than or equal to 0, right? That's good. Yeah, it's true. And finally, how about this one here? Sure, give me a witness. 3, 2, yeah, exactly. Very good. Let's say I got here, let's say 3, 2. So 3 here, 2 also there. And also I'm saying 3 less than 2 or 3 larger than 2. Apparently, this is true, right? And also this guy here is also true for the range. So overall, it's true. Kind of informal, but I think it does really give us some flavor about how we can prove it more formally. But we'll talk about it very soon. Okay, that's the example. So you guys pretty much know about how to judge it. And as I said, on Monday, we'll see more. We'll see some example for nested quantification. So let's say for Monday. Also remind myself. Examples on nested quantification. And we'll play with it. Okay. All right, that's good. All right, so we have done the examples here, and then we'll talk about proof strategy. How about that? Okay. Why don't we go over the proof strategy quickly, and then we'll take a short break, and then we'll continue. Okay. Proof strategy. And on the slides, just to show to you, on slide number 9 and slide number 10, you will see example on the first half. And for proof strategy, it will be on the second half. I'm going to go over them with you from scratch. Okay, that's also very important for you to know. Okay, and then also on slide number 10, that one is about the other quantification, right? We're going to go over this. Okay, so let me go over definition, and we'll do the exercise right after the break. Let's now do that. Okay. Let's now talk about basically 4 cases. As you can see, we're talking about for universal quantification, how do we prove it versus disprove it? And similarly, we got existential quantification, how do we prove it versus disprove it, right? That's kind of organization. And somehow, symmetrically, in some cases to prove universal, it will be harder. But in the other case, to prove existential, it will be easier. You kind of see. I'll highlight it when we get there. All right, so let's say, how do we prove this one here? How do we prove the universal quantification? Basically, to prove it, you got to focus more on the implication predicate here, because that one really tells you the nature of the quantification. Okay? So now, the way to prove it would be, let's try, for implication, in order to make it true, how many ways are there, right? The non-trivial way to make it true is when you got true over here and you got true over here. I somehow have to assume the range is the case so that I can consider all the values in the range. And using that assumption, I want to show that this predicate property here is true. All right, so that's the first way. Assume Ri to be true, so as to consider all the values that satisfy in the range. By assuming this, so as to consider all values in the range. That's basically assuming the antecedents. I'm pretty sure you have heard about it in 1090. All right? So by assume Ri and then show P of I. Okay, that's the first one. Pretty concise. Once we assuming this, so we can consider all the possible values in the range, whether or not each one of them is going to satisfy P of I. All right, so the second way will be the easier way. The easier way will just be if you can somehow show that this is an empty range, like an empty array, then you're good. Because there's no such value in the range that can show otherwise. So it's got to be true. All right. So number two will be you want to prove that it is not the case that R of I. Or equivalently, you want to show that it can be reduced to false. R of I is simply equivalent to false. And using our analogy, it's like an empty range. And I would say number two here is not a bad case to run into. You'll be running into that quite often in some edge cases. So let's definitely have to be aware of that. All right. All right, that's about proving it. And let's talk about disproving. How do we disprove the universal quantification, right? In order to disprove it, of course, we somehow want to show that the implication is actually false, right? What we got to do is, well, any idea? In order to do that, turns out to be the easy case. Here we are saying that it will be only true if everything in the range will satisfy this. It will be false if we can find a single witness that's actually in the range, but is actually going to violate the property. That's actually going to give us the true implies false case. All right, that's kind of what you got to watch out for. So I'm going to write down here. So there's only one way to disprove it. So you have to give a violation witness. I. So I is a concrete value you have to give to really disprove it. I should be such that it's going to make this implication false. Okay, to really make this implication false, and that correspond to the only row in the truth table that's going to give you false, right, for implication. So that one there is going to be R of I is true, but not P of I. Right? The I that you choose to give is such that it's going to make this true and it's going to make this false. So you got true implies false. Okay? So this one here is going to give you the true implies false for this one here, which will be equivalent to false. Right? There's only one way there. And this is really what the model checker is actually going to give you about a counter trace. Remember, when we are checking the invariant property, as I said, we're trying to say that for every reachable state, that invariant property must be satisfied. How does the model checker kind of disprove this particular invariant property? Then it's going to give you a particular witness state such that the state is in the reachability graph. It's one of the states. And then it's going to violate the invariant property. Right? That's just one instance. So this one here, you want to think about the counter example case for model checker. So this is, think about the counter example or counter trace given by a model checker. Right? So this case here is actually very important. How do you disprove the universal quantification? All right, so we're done with the universal about proving and disproving. All right. Let's now talk about proving and disproving, but for existential. All right. For existential over here, it's kind of similar to the disproving for universal. You also need to find a witness, right? In order to find a witness, it must be that you actually satisfy this and also satisfy that. Almost the same, right? Got to be watch out for. So that's why these two quantifications are rather related to each other. So for this one here, we're going to just give a, I will call satisfaction witness. I. And both of them must be true because we got a conjunction over there. So that one there should be R of I and P of I. So in that way, we're going to get true and also true, which is equivalent to true, right? Because we got this. So you really want to compare this and this. They are very similar, right? One is about proving the existential. The other one is about disproving the universal, right? They are very similar. All right, let's now do a final one before we take a short break, okay? Final one. How do we disprove? Disproving the existential will be harder than proving it. Because thinking intuitively, existential says that there should be at least one witness I can find. If you somehow you want to say, oh, there's no such witness, then you can argue that for all such possible value for I, none of them can be the proper witness to show satisfaction. So in some ways, it's a harder problem to solve. So this guy over here will be somehow similar to this one here, somehow similar. But we're going to see exactly. All right. So when you kind of study, you can maybe somehow try to maybe study in groups. So these two are kind of similar, these two. On the other hand, these two are kind of similar. All right, that's what you can do. Okay, for the other two, let me now put too many highlights. Okay, let's talk about the last one. All right, for the last one, let's see how we can disprove it. Because we got conjunction here. How can we make a conjunction false, basically, right? Well, apparently, case number one, I can just make the left-hand side false. Then it will be false anyway. I don't even need to worry about the right-hand side. Okay? So number one, show not R of I. Show that the range itself is actually false, is empty. Because if the range is empty, there's no way you can find a witness for satisfaction. Empty range, no way to find a satisfaction witness. All right, that's the easy one, the easier path, just to show that the range is actually empty. But what if the range is not empty? This will be the harder case, actually. This means if I somehow know that this range, if I somehow know that the range over here is not empty, that means I have to go through every value in that range and then show that none of them can be the proper witness, meaning that none of them is going to satisfy P of I. So that overall, there's no such witness. Okay. So what I will need to show is R of I and not P of I for all I that satisfies R. So I'm going to consider all the values of I in the range, and all of them are simply going to violate the property. So there's also no such witness. Okay. That means none of them, i.e., none of the values in the range can be an appropriate witness, can be a valid witness. The values in range can be a valid, sorry about that, I'm just going to finish here, can be a valid satisfaction witness. All right, so these four strategies are very important. Just make sure you kind of think about them, convince yourself. So when we write into any one of them, we can also apply them, right? Very important to see how we can do that. Any questions? Yeah.
Just that last line. Can
Yeah.
we say represented as like for all I elements of it are I?
Yeah, you may do that too. Because in that way, you're more like a converting between the two quantification, which we'll do as well. So what John was saying that, can you somehow express strategy number 2 by using for all? Yes, indeed. I'll just mention verbally. You can say for every value in the for every value I that satisfy R, it is such that they all dissatisfy the property. You can definitely do that. But for now, we'll just keep it a little bit more like a concise form. We can do that for sure. Yeah. All right, guys, why don't we take a short break, and then after break, we'll do some exercise. And we are getting very close to the end of the review. All right. All right, so before the break, we spoke about the different strategy. Let's now just apply them very simply, just to different examples, so you will see some idea. Simple ones. All right, so for each one of them, we got 2 for all. We also got 2 existential over here. And then for each one of them, I want you to decide, number 1, whether you want to prove it or disprove it. Whatever you choose, give me the details. All right? All right, for the first one, do you want to prove it or disprove it? Anyone? Prove it? Okay, so okay, prove it. Good. I agree. You want to prove it. Okay, give me some details. How do you prove it? How do you prove universal, right? So if you recall the 2 strategies, yeah, go ahead. How do you prove it? Every single case. So in this case, what will be the every single case? Can you enumerate them?
From the set of
1 to 10. Yeah, exactly. You got 10 different cases to worry about, right? Okay. So in this case, let's just remind ourselves very quickly. In order to prove the universal quantification, either you will show that this range over here is empty. Apparently it's not. this range contains from 1 to 10, 10 elements. But here, as your fellow student said, exactly right. So now we got to try the second strategy for proving it. For all the values in this non-empty range, every one of them must satisfy this property here. That's the second way of proving it, right? So what I would say is, so for this one here, this is non-empty range. Non-empty range, which will be go from 1 to all the way to 10. And obviously, each one of them is simply larger than 0. All right? That's how you prove it. Each simply larger than 0. That'll be enough. All right? It definitely is convincing enough to prove it that way. All right, very good. How about the second one? Do you want to prove it or disprove it? How about you? Disprove it? You want to prove it? Sure. How would you prove it? Oh, second one, not the first one. Second one. Okay, anybody? Anyone else? You want to prove it?
If we prove it's the same as number 0.
Okay, no, let's focus on this one here. Do you want to prove it or disprove it?
Disprove.
You want to disprove. Okay, give me the detail. How do you disprove it? Well, if you want to disprove it, right, you somehow want to show that this implication is false, right? So if you want, give me more detail. So if you want to disprove it, you got to give me that witness, right? What will be the witness? Yeah, disprove it. Yeah, exactly. Give me that witness. 1. Yeah, exactly. Yeah, guys, it's simple. Yeah, don't overthink, right? This is simple. All right, we're going to disprove it. This is non-empty range. So we're going to get the witness will be 1. So 1 is going to, so 1 is a natural, sorry, not natural. 1 is an integer, and also 1 less than equal to 1, less than equal to 10. So this one here is simply true, right? So it's in the range. Implies 1 larger than 1, which is false. So we got true implies false. True implies false. It's going to be false. All right? That's a witness. Only one witness. Okay? So that one will be disproving it. Okay? Okay, that's good for universal. Let's talk about existential. Oh, okay, good. You're ahead of me. Okay, you want to prove it. Okay? So if you want to prove it, give me the witness. Okay, just 2, for example, right? All right, guys, this one's not difficult. You basically just want to find in this, if this range is not empty, which we agree. Let's say 2, right? So this one over here, we can just choose the witness 2. All right, so 2 in integer and 1. And this part here for sure is true. And then, and also 2 larger than 1. That part is also true. So we got true and true, so that'd be true. Witness, very good. And the final one, disprove it. And this will be the harder case for existential, because somehow the range over here, the same range, is not empty. If you want to disprove it, you somehow want to show that every value in this range is going to not satisfy this property, right? All right. Hopefully, these examples will somehow reaffirm a little bit your understanding. So I want to disprove it. So this part over here, this is how I will write it. Somehow you want to show that there's no such valid witness that can show the satisfaction of the property. So you would say that all values in the range, which will be 1, 2, all the way to 10. All these values over here, all these values, okay, let me say it this way. Larger than 10 is just false. If you have better wording, feel free, but we just want to see the idea over here. You want to argue that each value, how about each value? That might be slightly better, not all values. Each value. So each value in the range is going to make the larger than 10 predicate false. That is, no valid witness can be found. All right, so that's good. All right, any questions? Good, okay. We got about 13 minutes. I think we can still do a few things. Okay. All right, so that's good. These are the exercises that we just did together. And let's now talk about quantification, switching. Okay, so here let me talk about, we can do a little bit proof just to give you one more example about the equational style, which you guys will be required to conform to for parts of this course. Okay. So before that, let me just talk about something very quickly, okay, about the two quantification. And this is also important to clarify. So we talk about the general forms of the two quantification. For all, and there exist, right? The general form. This might be more or less the form that you actually see more often, maybe back in 1090, okay? So the way we do that is we say for every x, so rather than having that implication pattern, you just have some predicate, p of x. And the general form for existential also similar. This is the most general form. However, our pattern, the pattern that we use in this course for TLA plus, and also the pattern you use for Rodin in 3342, they are not inconsistent with this. They are quite conforming to this. Okay, they're just like a special case. Okay, just for your information. For example, if you take a look at just one example here. So if you got things like there exist x over here, and then if you say let me just do another one here, sorry. If I say for every x, maybe x is an integer, and also 1 less than equal to x, less than equal to 10, implies x larger than 1. Right? If you think about this one here, somehow you can think about what we are doing is we have this form. So this one over here, oh, sorry. So think about this guy here is a single predicate to consider. So think about this guy here is like this guy here. Right? But just in this course, in order for the tool to be to accept that and do some processing behind the scene, we have to follow through this kind of pattern here. Right? But they're really the same. Okay? Just to show to you. And there are two axioms that we assume, which we're going to use to do a little proof together quickly. Okay? So the axiom that we assume will be these two. Okay? So if I say for every x, px, how do I convert that into the other existential quantification? If I say every x satisfy this, what will be the negation? That means there does not exist any x that does not satisfy p, like a double negation. Okay. Okay. Oh, sorry, I forgot a negation there. If I say everybody in 4315 passes, it would be as if I said there's nobody in 4315, that does not pass. That's true, right? Yeah, good. That's one way to think about it, double negation. Similarly, if you try also there exists x, you also put some property over here, equivalent to, also double negation. If you say there's at least one guy in 4315 who got A+, then what does that mean? That means it's not the case that everybody in the course does not get A+, at least one guy. So at least one guy. It's not the case that everybody does not get A+. You can think about it. Not the case that everybody in the course does not get it. Right, so this conversion here is pretty important, right? We're going to use these two axioms to prove something about the patterns that we are using for this course, right? Like involving implication for all, and also conjunction for existential. All right, that will be maybe the last, maybe one of the last things we can do today. And we just got 2 more exercises to go through for review, and then we're done. All right, let's now try this proof together. Oh, the proof will be here. So why don't we try the first one over here, right? The second one there, I'll leave that to you for exercise. The first one. All right, the first one here, we're going to do it together. And the second one here, I'm going to leave it at the bottom here, right? You guys can try. Okay, this one here. And the way we're going to proceed with that is we may have to use the axioms that we just spoke about. All right, so just don't forget, we got these 2 axioms over here. Okay, these 2. Maybe one or maybe both. And we want to show that we want to start with this. And then we want to end with the right-hand side. And because we got if and only if to show, we want to make sure every step over there is like an equivalent step. Every step. But we're going to show that. And the style, let me just mention again, is called the equational style of proof. That means every step should be equal to each other. And also you got to make sure you justify every step. So we're going to do equational style. All right, this one here, and let's now do that. Let me just repeat the starting point. Okay. So what I will do is I'm going to start with, for every x, I got R of x implies P of x. We'll start with this. Our goal is to somehow arrive in a form of this using existential. What we can do right away is to somehow convert from for all into exist in the first step. To do that, we can use this axiom here. We can go from for all into they exist with a double negation, right? That's the first axiom. Okay. So the beauty about equational style is you got to justify every step with the detailed reasoning. It is so important. All right, so let me show you. And you can think about this. This is the predicate part. This part here is the entire predicate. So you can, let's say this part here, just call it Q. All right, this whole thing here, just call it Q. So Q here is like the P here. All right, just the entire, like a body or predicate part for the universal quantification in its general form. All right, the first step here, we're going to say this one is equivalent to, and let's now give some reasoning right here. So we're basically saying the axiom. If I got for every x, and then I got qx, right? The qx I'm talking about over here. that would be simply equivalent to, according to the axiom, double negation. There does not exist x not q of x. Okay, double negation. And if you like, you can also put parentheses right here. Just to be very explicit, the negation applies to the whole thing. It's quite obvious, but I'll put it anyway. All right? So this will be the justification step that we need at first. All right, and then we should really get the following. There does not exist x, and then, not the case, r of x implies p of x. Okay, like that. And good, because we are moving much closer. Now we got existential. And we got negation here, negation here. So we got to play with this part over here a little bit, right? So why don't we try to simplify this implication? Because somehow we got and, but we got implication. So there is a theorem we talk about for the definition for implication, right? Remember? Okay. So we can now say the something we know, like a theorem. We know that P implies Q is equivalent to not P or Q. All right, and let's do that right away. That's going to give us not exists X, not Rx or P of X. We're getting very close. All right, and then. Guys, any suggestion? How to move on? We're getting very close. De Morgan? Ah, good. Because we got negation here outside, right? Good. Awesome. Let's do that. We got 2 minutes. We can finish this. Okay. Equivalence, and then we got De Morgan. Basically, we want distributes not over or. Not P or Q is equivalent to not P and not Q. And let's say for this one here, we also do double negation in the first step. Sorry, at the same step. Typically, you should only do one application at a time. Yes, but now I'm running out of space. So I'm going to do 2 at a time. But for you guys on the exam, you got to do 1 step at a time. Okay. And also double negation. Not P is equivalent to P. All right. So what I will do is I still got not there exists X. I should really get here not Rx. Should be Rx, right? Also, I got and, right? Because I already got and over here. And also not Px. All right, that's exactly what I need. All right, you can see here, that's the destination I was looking for. And that's the starting point of my proof. All right, so you got to make sure every step is justified. Let me do a recap for a few seconds and then we're done. Basically, I think the main thing for you to pick up over here will be, of course, the basic property about quantification and also implication, etc. But this style of presenting the proof is something you will need ultimately. But we'll just keep doing it this way so you get used to it. Make sure you start with something here, end up with something, and in all the intermediate steps, you also always have to justify. Okay, thank you so much. And then make sure you submit lab number 1 in time, and then I'll see you next week.